Hello, my name is Rob Durham, and I'd like to welcome you all to the inaugural edition of the Gyrolab Spin. This is a video podcast where we're aimed to talk about things that are important to the bioanalytical drug development community and people who are Gyrolab users in particular. I'm joined today with my friend and colleague, John Chappell, and what we'd like to do today is talk a bit about how the system works and some of the key features and benefits to the Gyrolab system compared to a typical immunoassay. John, welcome to the podcast.
Hi, thanks, Rob. As Rob mentioned, my name's John Chappell. I've got a lot of experience using the Gyrolab as a user. And the main thing for me was the Gyros just allowed you to develop assays very quickly. The fully automated part of the platform, but also the quick time to result, only an hour from starting an assay to get to actually seeing your result, was a big thing for me, allowing me to develop assays very quickly. And I think that the technology is very cool, and I think it is a lot of advantages over a plate-based ELISA.
Yeah. That's great, John. Thank you. And as John said, I was also a customer before I joined the company. I've been here now for about 12 years with Gyros, but prior to that, I was a scientist at Pfizer, and we adopted the platform in my lab because of the speed with which you could do the assay development. So what I'd like to do now is sort of shift gears here. We'll show some slides and talk a bit about how the system works and how you can achieve these enhanced benefits on the gyro system versus a plate-based system. So our agenda for today is really talk about the automated immunoassay at the nanoliter scale, and then once we've delved into some of the basics of how the system works, I want to talk about some new functionality that's been added to enhance sensitivity for doing biomarker work on the Gyrolab platform. So as you can see here, we have both the Gyrolab Expand and the Gyrolab Explore. The Explorer is our 1 CD at a time instrument and is used quite a lot for folks that are doing just assay development. They don't have very high throughput needs. When I was using the system initially, we only had the 5 CD system, so I think the 1 CD at a time system is really a useful tool for those people that just don't have the high throughput needs. What's your take on that, John?
Yeah, and I see the one CD instrument as something where you can actually load CDs constantly as well. So when you're running the instrument, you can be preparing your next run to actually run, and it's quite good, particularly for running during the day. Probably where the 5 CD system really excels is being able to run CDs overnight. So you can set up CDs within the day to run overnight. You can go home and then you get results back the next morning. That's really where I see the big advantage of the 5 CD system.
Yeah, exactly. And we've got a number of customers out there that use this as sort of their second shift, right? So they'll do a big 5 CD run, hit go, and then go home for the night. When they come back the next day, they're able to maximize the utilization of the system and maximize the throughput. One of the hallmarks of both systems, though, is this sort of CD assay plate technology, which is really the heart of both systems. This is the key to being able to miniaturize and automate the system. We'll talk more in forthcoming slides about how it all works together. But give us your take on, using the CD as a way to do your assay development, John.
Yeah, I mean, the CD gives a lot of flexibility. I mean, there is segments of 8, so effectively you can actually optimize conditions in segments of 8. So you can look at different capture and detection antibodies, and because it's fully automated, to setting up a checkerboard experiment is very, very quick on the system. And because you're also letting the system doing the pipetting. Sure. So the problem with doing checkerboards when you do it manually, it's so easy to actually mess up the pipetting. Yeah. So that part is actually completely taken away from you.
Yeah.
I think the other advantage of the 5 CD system as well is that if you have any reagent or sample instability, for example, then the onboard sort of refrigeration actually helps stabilize the samples. So that's a big advantage.
Yeah, that's a really good point, and that whole DOE point that you made too is really interesting, because you can do your big design of experiments, and the instrument doesn't care if you come up and talk to it while it's pipetting, right?
Exactly correct.
Excellent. Here you can take a look inside the system. This is inside our 1 CD at a time Explorer system, and you can see there's a place for our microfoil covered plates. These are 96 well PCR plates, which really are the sample handling and reagent handling wells for the system. We've got our liquid handling robot, which has needles that transfer the liquids from this microtiter plate onto the surface of the CD. And then you can see here our CD is clipped in, and with the 1 CD at a time instrument, you can see that there's a robot here which moves up over the CD, and that does all of the liquid transfer and the reading the CD functions.
So moving on to the 5 CD system, the big difference here really is that there's a system for moving the CDs around to put it into the assay position. There's also positions for multiple microtiter plates where each assay is set up. So you can have up to 5 CDs and 5 assays running simultaneously. The difference really is that it requires compressed air, and compressed air is to drive the movement of the CDs, and this moves it into the home position where the needles and reagents and samples are transferred onto the CD.
Yeah, and as you mentioned earlier, you can see here there's also cooling possibly for the microtiter plate positions.
And there's cooling blocks really to maintain the temperature, which can be quite important if for a CD run, which is going to take around 5 hours.
Yeah, I think a number of folks asked for this for years, and we finally
I was one of them.
Yeah, I finally delivered it in the Expand, so it's been a really good a feature for the Expand system.
This will really show you how to do the assay setup. So first, the software will tell you where to place the samples, standards, and the reagents, and which wells they're placed in. If you had multiple antibodies to screen, these would just be added into single wells. So it gives you a lot of flexibility in terms of your assay setup. And then it tells you exactly what volumes are required. So this tells you the minimum volume. So as you can see, the standards for this assay setup, you only need 4 microliters into the microtiter plate. It tells you exactly how much detection and capture reagent you need. So it gives you exactly the information and exactly which wells to place it. And then this is placed onto the instrument, and then you walk away from the instrument, and the instrument will generate your results.
Well, one of the key differences between the gyro system and a typical plate-based ELISA is the CD, so the CD-shaped assay plate. And so we'll spend a little bit of time talking about how that works and why that's so important for automating and miniaturizing immunoassays in our system. So this shows a picture of the bioaffy CD. We have a range of different CDs, which we'll talk about. But all of them are organized in groups of 8 microstructures connected by a common channel. And by microstructure, I'm showing here now, if we focus in, we can see 3 of these microstructures adjacent to one another. And you can see in blue there, 1 microstructure that's been highlighted. And that really equals 1 data point. So it's the equivalent of a well in the system. So John, you alluded to the fact that we're working in groups of 8 on the system. So when you're thinking about this in terms of how you do your assay development, you want to be thinking about these individual microstructures as sort of 1 data point, 1 microstructure sort of a format.
Yeah, so I would normally put a standard curve in the section of 8, so 1 blank and 7 standards, and that allows you there to vary in that each segment of 8 a different antibody concentration, capture and detection. So it gives you automatically 12 different conditions generated per CD.
Yeah, absolutely.
So it allows you to screen reagents very, very quickly to see, and also because you're doing a full standard curve as well, you can really see how that affects your assay range. Because a lot of time with checkerboards on plates, you're doing miniature curves, but this allows you to really look at the analytical range at a very early part of development, which I think is very important.
Yeah. Yeah, then you can see here as we continue on down the flow through is really the unique feature of our system is this flow through affinity capture column. So in a static ELISA plate, you may run into some matrix effects and things like that, and one of the advantages of using this flow-through design is it tends to minimize matrix effect. We don't totally get away from it, but I mean, you can see matrix tolerance be a big benefit to using the gyro system.
Yeah, you can normally get away with very low minimum required dilutions compared to an ELISA, and it's definitely a distinct advantage.
Yeah, and I think that really helps with sensitivity, right? If you don't have to dilute your samples as much, especially if you're working in biomarker space, sensitivity is king, and so not diluting your samples very much is really useful. The other piece of this I think is important is that you can see here we have these polystyrene streptavidin coated beads, and this chemistry really gives us the flexibility to make any sort of a ligand binding assay on these beads. We just simply need to have a biotinylated capture reagent, and in conjunction with a fluorescently tagged detection reagent, we can build an immunoassay for a analyte that we're interested in.
Yeah, and you're not limited just to a sandwich method. You can go competitive, you can go indirect, you can go double capture, double detection. We can provide methods that you can basically do any assay format that you're currently running. We can try and automate it onto the system.
Yeah. Yeah, in our system we have automated methods that are run, and it's sort of like the protocol you'd follow if you were doing it manually. But our automated methods will, truly automate the process of doing the steps of your ELISA. And in many cases, on a typical CD, it's between 45 minutes to an hour to run, and I think that's huge compared to 4 to 5 hours for a standard plate-based ELISA. This next figure, what you can see is a layout of the common channel and a few of the microstructures, and the important point here is the hydrophobic barriers, I think. What those hydrophobic barriers do is allow you to take advantage of capillary action to draw the samples and the reagents into the microstructures, and then hold back the liquid until you spin the CD, and only when you spin the CD does it deliver those liquids to the affinity capture column at a fixed flow rate. And so that allows us to really do parallel processing, which I think is a huge advantage to a standard plate-based system where you can run into positional artifacts due to the fact that you're and timing artifacts due to the fact that you're adding things to the plate manually.
Yeah. And the volume is defined by the CD itself, and this is very important because you don't have the analyst to analyst variability. The actual volume is defined by the CD, and it's part of the manufacturing process. So you don't get variability and precision issues as a result of volume. And because all samples are processed in parallel, they effectively, you don't get any drift effect going on because everything's done at the same time because of the way that it's spun through the hydrophobic barriers onto the column. So you get very consistent data. And I think the other thing as well is that you can modify the assay range and just by changing from a different CD. So you can really change the analytical range from a very sensitive assay to a very insensitive assay, depending on the samples that you've got. And also this allows you to minimize sample dilutions and not necessarily waste precious samples. So yeah, it gives you a lot of flexibility.
Excellent. Yeah, I really like that. We have 4 different volumes now, 20, 200, 1,000, and now 4,000 nanoliters, and a couple of other flavors of CDs that we've added to the family recently. But in general, it's that ability to add volume to the same affinity column, which allows you to sort of shift the sensitivity curve to the left. So as you go from smaller volumes to larger volumes, you can really shift that sensitivity curve. What we've said in words, you can see more easily on this little animation that we've used to really describe the process. You can see here capillary action is drawing our common reagent, our capture reagent, into the common channel. It holds that 200 nanoliters back until we've spin the CD, and then delivers it to the affinity capture column, and thereby functionalizes that column with our biotinylated capture reagent. Next, you can see the liquid handler is delivering individual samples, and we actually overfill that sample volume definition chamber slightly. And then by using a low speed spin, we can spin off that excess through an overflow channel and then perfectly define the sample volume. It's 200 nanoliters in this case, which we can then use a high-speed spin to spin over the column and flow that over those functionalized beads at about 1 nanoliter per second. So that microfluidic design really eliminates some pipetting errors that you might have. Again, you can see here the common channel is used to deliver the capture reagent. Hydrophobic barriers hold it back, and then 200 nanoliters of detection reagent is added to each of the wells. And so as that flows over the column, then we'll actually complete our sandwich ELISA. And you can see a little figure down on the right. We've now completed our ELISA, and the next step then is for the CD to be scanned by a laser. So we have a monochromatic laser that scans over each of the columns. It takes about 90 seconds to scan an entire CD, and what you see here is the laser will actually rasterize down the column so that we get a 70 by 90 pixel image of the retained fluorescence on that column. So again, the samples are all processed in parallel, and those individual nanoliter volumes are really precisely defined, and that gives us really good control of the assay. So I think one of the things that we've talked about, John, is taking away some of the human element, the manual piece out of that really improves the robustness of an assay.
Yeah, it minimizes analyst to analyst differences, which unfortunately you do get when running immunoassays. I mean, it is a bit like immunoassays, a bit like gardening for me. You know, it's you need these subtle skills, and I think it takes away that bit of unvariability.
Exactly. You don't need the magic plate washer or the magic pipette anymore,
or the magic drawer, or everything else you need to get the assay to
Take
work.
some of the magic out of it, but it improves the process. Great. So after that CD gets scanned and all the microstructures are scanned with the laser, you can see here we can show a response versus concentration curve that could be either your quality controls or your calibrators. In this case, it's a series of calibrators with immunoglobulins, and you get a nice tight there's 2 replicates here across the range of this curve. But I think the real beauty of this system is you can actually go in and interrogate individual data points and look at what the binding pattern on the column looks like. So if we look at this one, for example, what do you see in there, John?
Yeah, so I mean, this is one of the great advantages of our system, is being able to look at the binding profile. You can see the affinity of particularly of the analyte to capture binding in the column. So this is a good sharp peak. You can also, if you get an outlier standard, for example, you'll see a very different profile in many cases. So it can be used for diagnostic purposes, but also can very much be used to show which assay reagents are working the best when you're doing reagent optimization. for this curve is pretty much perfect,
Yeah.
to be honest. So
Yeah.
this is a great presentation curve, but
Yeah.
you don't always get curves like this. And you know, it looks really good. And I'm sure if you see the bottom standard, you can see when you've got less binding, you can see how it relates to the calibration response. It's just a very powerful tool for assay development and for diagnostic purposes.
Yeah, and I think too, I think it's important to recognize that we've sort of rendered this column fluorescence signal in 3D, and so just to orient folks, so the direction of flow over the column itself is in the x-axis from left to right, so that's called the radius. In the z-axis across the top of the column is labeled as angle, since that's around the angle of the CD, and fluorescence intensity is the y-axis. And I think, yeah, it's important to point out that you see the system will auto scale the peaks, so sometimes you don't see a big difference in peak height, but here even you can see that the scale is different and that the height of the peak is reflected in the lower amount of analyte on there. I think the other piece here is this area there's a little square there that you can kind of see. That's the actual area that gets integrated, so that's the part that gets counted.
Yeah. It's such a powerful tool. It should be used more by people, because it's such a good way of seeing how your assay is working.
And we have these peaks happen to look really nice, but I mean, where it really shines is when things don't look so nice. It can tell you a lot about whether your reagents have gone off or whether your samples are problematic. The viewer is really a powerful tool. It really sets the gyro system apart from other ELISA type methods that are out there.
So again, here we really show that the volume definition chamber, and as has already been mentioned, you know, with different CDs, the volume of this definition chamber is different. So we go through all the range of our CDs from 20 nanoliter all the way from up to 1,000 up to 4,000. So the same sample can be loaded onto the different CDs and will give very different analytical ranges. So Rob, I mean, just to explain, if you go through the kind of the assay ranges, you can get comparisons with different CDs.
Yeah, I think if you look at the orange figure in the lower left, this sort of schematized figure of a standard curve, the orange figure represents what you're seeing on a bioaffy 200 nanoliter CD. And so if we note here, you can get sensitivity on this 200 nanoliter CD. It really is dependent on the capture reagent that you have, but you can get down into the single digit nanograms per mil on the 200 nanoliter CD, and then up to micrograms per mil. Now, if you wanted to improve the sensitivity, you can simply increase the volume of sample that you put over that same 15 nanoliter affinity capture column. So by shifting to the 1,000 in blue or the 4,000 in purple, you've added up to 20 times more sample volume over the same 15 nanoliter affinity capture column, and you can increase the amount of an analyte that you might accumulate on that column and therefore increase the signal.
Yeah, just a brief mention of the mixing CD, which is on here as well. So the mixing CD is based on the 200 nanoliter CD. It was really designed for anti-drug antibody assays, where it has a mixing chamber and allows you to do an acid dissociation and fully automate this as part of the assay. So you take your sample, it will acidify it, then neutralize it, and then that's run over the column. So this CD is very flexible. Actually, it's very good for assays where you want to increase the contact time as well by pre-incubating them in the mixing chamber, as well as things like competitive methods and other formats. So I love the mixing CD. It's one of my favorites because it gives a lot of flexibility in terms of assay formats.
It does. I think the only caveat there is you have to remember that it is based on the 200 nanoliter CD, so you're a little bit more limited in terms of sensitivity. But in terms of the upfront, being able to manipulate those samples in a consistent way, that's where it really shines in an anti-drug antibody method.
That's completely agree. Yeah.
So after that discussion about how the Gyrolab system works, we thought we'd use some examples with the advent of the 4,000 nanoliter CD. It's really enabled some additional work on the biomarker application. And so here you can see the interleukin-2 assay on the Gyros system. On the 200 nanoliter CD, you're seeing the curve in orange, and as we shift to 1,000 in green and the 4,000 in blue, you can see that we're getting that consistent shift from right to left in the sensitivity curve, and this is going to improve the overall sensitivity of the assay. So, you know, John, you and I have done a lot of work on biomarkers in the past, and, you know, really, I've used the Gyros system for biomarkers, mostly for Alzheimer's disease biomarkers in mice, but, you know, when you're looking in CSF, sensitivity wasn't an issue, but it's when we get into the periphery.
Yeah, particularly measuring these in the blood at really low picogram per mil concentrations. This is really where the 4,000 nanoliter CD allows us to measure low picograms and, you know, high femtogram concentrations of analytes suddenly.
Exactly, and while it, you know, realistically, it doesn't going to approach the ultra sensitive methods that you have with other methodologies out there that get you the really super ultra sensitive methods, but I think it has a place.
Yeah, and also because we're really focusing on developing single biomarker assays, which are easier to validate, going through normal sort of bioanalytical validation processes, and you tend to get more robust and reliable assays and easier to validate in this type of format.
Yeah. So I think one of the key things to look at here too is, you know, this is where the viewer really enables us to have a look. So if we take a look, you can see here, looking at the viewer profiles from each of those three curves. Yeah, what do you think there, John?
Yeah, so you can see that the dramatic increase in sensitivity from going from the 200 nanoliter, where you can barely see any signal in kind of the background viewer response, and then you see in the 1,000 you can see an improvement in the sensitivity. You can very much see it come in from the background, but then when we look at the 4,000 nanoliter, now we've got a really big defined signal. So we're seeing a dramatic increase in sensitivity, and effectively this isn't really with not much increase in volume either. So it's, you know, and, you know, depending on what you're using the assay for, you know, there are times when biomarker levels can be huge when you need a very insensitive assay, but a lot of time we need a very sensitive assay.
Yeah, I think for the 4,000 nanoliter CD, typically it's going to ask for about 12 microliters of total diluted sample for a duplicate measure.
That's correct.
So you're not really sacrificing a lot on volume. Relative to the Gyros system, it's a big increase in volume.
Yeah.
But and then here, I think too, is where it really shines, because now you're looking at the bottom point of the curve. We're at about 1.3 picograms per mil, and you can see that for both the 1,000 and the 200, we're kind of at background.
Yeah, and we can, with the 4,000, we can probably think of that our LOQ is going to be around the 1 picogram per mil.
Yeah. Yeah, so I think this really shows the principle. I mean, I had that schematic on the previous slide, which shows theoretically how things could shift if we increase the sample volume. But here's where the real assay, you really see it.
Yeah, exactly.
The theory is proven out. So to talk about our IL-2 assay in a bit more detail here, we've got a set of quality controls that range from 0.6 picograms per mil all the way up to 2,000. And I guess the thing that jumps out at you here is that certainly we're getting really good performance across the range. Probably our 0.6 is going to end up being an anchor point. But somewhere between 0.6 and 2, we'll probably have our LLOQ in the assay, probably.
Yeah, no, I mean, it could, yeah, as you say, it could be between 0.6 and 2, maybe around 1, based on this data. But I mean, we've got a really big analytical range, great CVs, and also good total error. So really shows really good assay performance.
Yeah, and I think this bears out the point too. It's fine if the curves look pretty, but if you have quality controls that deliver, that lets you know where the real assay performance is.
I think one of the problems with cytokines is getting QCs, particularly in samples with significant levels, and sometimes you need to use hyperimmune stimulation to produce levels of cytokines to measure, and that can be one of your problems when you're trying to validate these type of assays.
Exactly.
As I mentioned earlier, so we can't really multiplex on the Gyrolab platform, but with the 5CD system, it is possible to run 5 analytes simultaneously from the same sample in the same run. And this is an example where we've looked at 5 different cytokines, and also looked at them run on different CD types as well. So these have been run simultaneously. We've looked at all the 200 nanoliter CDs together, then the 1,000 and the 4,000, and you can see in every case that we've improved sensitivity, moving from the 200 to the 4,000, and in every case as well we've got sensitivity around the low picograms per mil for all the cytokines.
Yeah, I'd agree. And to the multiplexing question that comes up all the time, people want to know, can you multiplex? But I always ask, why do you want to multiplex? It does create some challenges if you have a highly multiplexed experiment in a clinical setting. But for me, the gyro system really shines when you've identified 3 to 5 features that you really want to measure in your samples, and you want to do it in an automated way, robust, singleplexed individual assay, and you just really multi-sampled.
Yeah, I mean, multiplexing can give you a lot of information. It can give you information on large up or down regulation. But for me, particularly as you go into the more regulated phases of your drug development, you want more validated assays, and you want to look at smaller panels of markers. And this is when hopefully we can very much, help with limited sample volume generate a lot of data.
Excellent. So here you can see that we have assay protocols for several cytokine biomarkers and some PK assays. These are available on the website. This will allow you to facilitate your own assay development. You can see how we've done assay development for a variety of different assays. Also, John, I know that we're developing kits for some of these cytokine biomarkers, but I think folks can get access to some of the labeled reagents if they wanted to really speed up their own assay development.
Yeah, no, please contact us for any further information, and we can see how we can help. I mean, these assay sheets really give an indication of assay performance, including analytical range, and hopefully will allow you to set up these assays in your laboratory.
Yeah, I think the idea here was to sort of do something that would really facilitate folks taking up the system and using it for assay development without going to the extent of having a fully developed, validated assay kit that's available off the shelf. Certainly we're working towards that end, but this gives you an intermediate opportunity to sort of do some assay development work.
Thanks everyone for your time. Please contact us if you have any questions. We've included our contact emails here, and please do not hesitate to contact us.
Yeah, thanks. It's been a pleasure having this conversation with you, John, and I hope this is useful for folks out there. And in addition to your questions, we'd really appreciate your feedback. And if there is a particular topic you're most interested in, we'd be happy to put together another conversation. So thanks. Until next time.